Computers are pretty simple at their core. Everything is just on or off, a 1 or a 0. But our world is full of numbers that are way more complicated. Decimals, fractions, all that messy stuff in between. So how in the world do these simple binary brains handle all of that? Well, that is the exact puzzle that we are going to solve today.
I mean, that's the big question, right? How can a machine that sees everything in black and white possibly grasp all the infinite shades of gray in a number like pi? It feels like it shouldn't work. But our computers do it trillions of times a second, and the secret, well, it all comes down to a really clever, globally accepted system.
And that system is called the IEEE 754 standard. Seriously, this is the unsung hero of modern computing. You can think of it as a universal translator that lets every single computer, from the smartphone in your pocket to the massive supercomputers at NASA, speak the exact same numerical language.
So here's what we're going to cover. First, we'll look at the decimal dilemma. Then we'll dive into the big idea that solves it, binary scientific notation. We'll break it all down into its 3 key parts, and then actually build a number using the 32-bit blueprint. After that, we'll see how to get even more precise with the 64-bit version. And finally, we'll wrap it all up with why this standard matters. Ready? Let's do it.
Okay, so let's start with the big problem, the decimal dilemma. See, we humans think in base 10. We have 10 digits, 0 through 9. But computers only have 2, 0 and 1. Now, representing a whole number like, say, 9, that's pretty straightforward in binary. But what about the 0.75 in 9.75? How do you even begin to represent that with just ones and zeros? Yeah, that's where we need a completely different approach.
And here's the genius of IEEE 754. It doesn't even try to write the number down literally. Instead, it uses a concept you probably remember from science class, scientific notation. The only twist, it does everything in base 2, in binary. And that one simple idea is the key that unlocks this whole system.
I love thinking about it this way. It's not just a set of rules. It really is like a universal recipe. A recipe for creating almost any number imaginable, but you've only got 2 ingredients to work with, a 0 and a 1. And like any good recipe, it's got 3 main steps, or in this case, 3 key parts.
So how does this recipe actually work? Well, every single number that has a decimal point, what we call a floating point number, gets broken down into just 3 simple pieces of information. It doesn't matter if it's 9.75 or -1 billion, it's always these same 3 parts. So let's break them down.
First up is the sign. And in this one is about as simple as it gets. It's just one single bit. Think of it like a light switch. If that bit is a 0, the number's positive. If it's a 1, the number's negative. That's it. Super easy. All right, next we've got the exponent. This part is all about the scale of the number. It's basically the zoom lens. It tells the computer where to put the binary point. A big exponent means we're zooming way out to a really, really large number. A small or negative one means we're zooming way in on a tiny little fraction.
And the third and final piece is the mantissa, sometimes called the significant. This is the heart of the number. It contains all the actual significant digits, and the more bits we can give to the mantissa, the more precise our number can be.
So here's how those 3 parts fit into a standard 32-bit number, or what's called single precision. You get 1 bit for the sign, 8 bits for the exponent, and a whopping 23 bits for the mantissa. You can really see the design choice here, can't you? The vast majority of the space is dedicated to precision, to getting those digits just right.
Okay, theory is one thing, but let's actually see this in action. We're going to take a simple decimal number and walk through, step by step, exactly how a computer uses that 32-bit blueprint to encode it.
Let's use the number 9.75. Okay, step 1. It gets converted to binary, which is 1001.11. Step 2. It's put into binary scientific notation, which looks like 1.00111 times 2 to the power of 3. Now from that, we can pull out all our pieces. The sign is positive, so that's a 0. The exponent is 3, which gets stored with a special bias. And the mantissa is just that part after the decimal, 00111. Finally, the computer assembles those 3 binary pieces into a single 32-bit pattern. And just like that, 9.75 is in a language the computer gets.
But sometimes 32 bits just isn't enough. For things like heavy-duty scientific computing or high finance, you need more precision. And for that, there's a bigger blueprint, the 64-bit double precision format.
But the great thing is, it's the exact same idea, just bigger. And you can really see the difference here. The core concept is identical. We still get just 1 bit for the sign. But now, check this out. We have 11 bits for the exponent, which gives us a way bigger range of numbers. And the Mantissa? It gets a massive 52 bits. That is just a staggering leap in how precise our numbers can be.
So just how big a range are we talking about? Well, a 64-bit number can represent values up to roughly 1.8 with 308 zeros after it. I mean, that's an astronomically huge number. It's hard to even wrap your head around it. And it's all possible just by giving a few more bits to that exponent part.
So, we've gotten a little technical, I know. But here's the really crucial part. Understanding why this isn't just some abstract computer science exercise. This standard is, quite literally, the bedrock of our digital world. Just think about it for a second. The position of every single object in your favorite video game? That's calculated using IEEE 754. The complex models that predict the stock market or simulate weather patterns? Same thing. Your GPS figuring out your location down to the meter? You guessed it. It is absolutely everywhere. Ultimately, that's what this is all about. Before this standard existed, it was kind of the Wild West. Every computer company had its own way of handling decimals, and it was a total compatibility nightmare. IEEE 754 created a true universal language, ensuring that a calculation on your machine will get the exact same result on any other machine in the world.
And that brings us to a final, fascinating thought. Even with 64 bits of incredible precision, we're still using a finite number of bits to represent what can often be an infinite number of decimal places. And this leads to tiny, almost imperceptible rounding errors. So the question to leave you with is, how do these tiny imperfections in a near-perfect system impact our world? Something to think about. Thanks for tuning in.